Okay, so we're going to be talking about polynomial functions, and so far we've talked about linear functions and quadratic functions. So now we have this idea of a polynomial function, which hopefully looks a little bit familiar. But if you recall, I could have a linear function like this, and I can have a quadratic function like this. And technically, both of these are polynomial functions. A polynomial function is nothing more than a function with multiple terms. And remember, terms are separated by plus signs and minus signs. So this first linear equation here, this linear function, that has two terms, and this quadratic has three terms, making them a binomial and a trinomial, respectively. Now notice what the difference is. I have this quadratic that has a degree 2, and I have this linear function that has a degree 1. Remember, when we have a degree or an exponent of 1, we don't write it, but it's understood to be there. Well, we could have any degree, and so in mathematics, when we have a polynomial function or we have a function with any degree, any stands, or any we use n for. So this n, it could be 1, it could be 2, it could be a million. And for a quadratic, you can see that we have a degree 2. The next exponent is 1, and then the following exponent is just 0, because this is 1, which is x to the 0 power. So as we go to the right, we are going to decrease this exponent by 1. So we have n minus 1, n minus 2, and we go on until we have nothing left, until we have just a single x to the first, and then finally some constant, which is going to be a to the 0. Now this a is going to represent our constant, and so this a to the first is some coefficient, and then all the way here I have a sub n. This a represents a coefficient, or in this case for a sub 0, a constant. This a sub n is just the coefficient for the variable x, and the subscript shows us which exponent it goes with. So this a sub n is the coefficient for x to the n. The next coefficient is a sub n minus 1, which is the coefficient for x to the n minus 1. And then we have a sub n minus 2, which is the coefficient for x to the n minus 2. And that's a general form of a polynomial function. We use subscripts and we use these variables to show us that we can think of any value for n, and it's going to fit into this. So for this quadratic, we can see that n is 2, n minus 1 is 1, and then the last term here is n minus 2, which is 2 minus 2, which is 0. Now the constant is this 2, which is very similar here. So this will work for any polynomial, for any n, for any a. Now for us, we're really going to be working with cubics. So y is equal to x to the third plus something x to the second plus something x to the first, and then plus some constant. Now if I put numbers in here, 4, if I put numbers in here, we can see what matches. So a sub n is 4, a sub n minus 1 is 2, a sub n minus 2 is 3, and then this constant is 0. We can skip a whole bunch here. This is written so that there can be an infinite amount of values here, but we can skip them as we want. Now we're going to be looking at functions and trying to visualize how they graph them, or how they look. So if I have this, y is equal to x squared, hopefully you can picture what this function looks like. It's a parabola, and it looks like this. We're going to be looking at end behavior. So end behavior means as the graph goes to the end, what does it look like? So for this parabola, as I go to the right side, the right end, what's happening with this function? It's going up to infinity. As I go to the left end, what's happening to the function? It's also going to infinity. So we have two situations here. We could have that the degree is even, or we could have that the degree is odd. We're also going to be looking for when the leading coefficient, so the leading coefficient is positive, and also when the leading coefficient is negative. And that's how I have this table here for possibilities, all the different combinations of even and odd degrees and positive and negative leading coefficients. So when I have a degree that's even and a leading coefficient that's positive, think of an example. We can think of that positive quadratic, that positive parabola. And so for us, as x goes to positive infinity, y will also go to positive infinity. Now as x goes to negative infinity, y will go to negative infinity. And so we can see that. And just like I said before, the end behavior, as I go to the right end, notice x is going to the right, so x is getting larger. It's going to positive infinity. Y is going upwards. It's going to positive infinity. And, whoops, y is going to positive infinity as well, as x goes to negative infinity. The ends are going in the same direction. So I got this all mixed up. My apologies. So when we have the leading coefficient that is negative, what we're going to have now is a sad parabola. Think about y is equal to negative x squared. And this will work for any even degree, such as x to the fourth, x to the 10th. And we can say that as x goes to positive infinity, y is going to negative infinity. And as x goes to negative infinity, y is again going to negative infinity. So you can see that as long as the degree is even, if the leading coefficient is positive, y is going to positive infinity in both directions. If the leading coefficient is negative, then y is going to negative infinity in both directions. And if you ever get confused about this or stuck, think about a parabola. A parabola is a great example. All right, well, what about when we have an odd degree and that's positive? Well, for an odd degree that's positive, again, we're going to have the two situations as x goes to positive infinity and as x goes to negative infinity. Well, we have an odd degree. 1 is an odd number. So we can have a linear function with a positive leading coefficient, so that's going to be a positive slope. As x goes to positive infinity, look, y is going to positive infinity. But as x goes to negative infinity, y is going to negative infinity. So when we have an odd degree, we're going to have opposite directions for the end behavior, where for an even degree, we have the same directions. When we have an odd degree and a negative leading coefficient, that's like a line with a negative slope. So as x goes to positive infinity, y is now going to negative infinity. As x goes to negative infinity, y is going to positive infinity. Again, see that not only the y movement is opposite, but the relationship with the x movement is opposite. As x goes to positive infinity, y is negative infinity. As x is negative infinity, y is positive infinity. This is kind of a crude sketch to help us out, but this is a great picture I stole from another textbook. And I think it's a really good picture, and it shows some different functions here. So again, when the degree is odd, we're going to have opposite directions for the end behavior. When the leading coefficient is positive, then x and y are both going to be positive or both negative. But when that leading coefficient is negative, then x and y are going to be opposites of one another, as x is positive, y is negative, and vice versa. With even degrees, they're going to go the same direction. So if the leading coefficient is positive, both ends will go to positive infinity. If the leading coefficient is negative, both ends will go to negative infinity. I really recommend you commit this to memory, but again, if you think of some examples, like for an odd degree, a line, or for a positive degree, a parabola, you can work this out on your own, and you don't have to spend hours trying to remember it. Now, one quick thing before we start graphing these is talking about real zeros. Well, real zeros are nothing more than x-intercepts. Now, there's an emphasis on real because we could also have imaginary zeros, which is not going to concern us right now. That does not cross the x-axis. Real zeros are where a function crosses the x-axis. So if you think about a graph with an x and a y-axis, what's true about this x-axis? This x-axis is where y is equal to 0. So for any polynomial function, you basically want to find the x-intercept. You want to make y equal to 0 and then solve for x. We've actually done this before with quadratics. So if I have, say, y is equal to x squared plus 9x plus 20, and I want to find the x-intercepts here, I make y 0, and then I solve for x. Now we can see this is a quadratic, so the way to solve this is to factor. And then once we factor it, we set each of those factors equal to 0. Getting ahead of myself there. So that means that x plus 5 is equal to 0, and x plus 4 is equal to 0. So we get x is equal to negative 5, and x is equal to negative 4. Just as I talked about before, though, these are lines, so we want to write these as points. Negative 5, 0, and negative 4, 0. Make sure that you write your x-intercepts as points, as x-intercepts. One important concept is a repeated zero. And a repeated zero is when we get the same solution twice. So same solution more than once, actually. We can have it more times. So let's say, for example, I have y is equal to x squared plus 6x plus 9. And I want to find the x-intercepts. Okay, so I make y 0 and I solve for x. X squared plus 6x plus 9. This is a quadratic, and we solve it. And actually, if we solve this, hopefully we realize this is a perfect square trinomial. Notice I have this squared. So I have x plus 3 is equal to 0, and x plus 3 is equal to 0. I get the same point twice. This means that when we have this repeated 0, this point is going to be a turning point, meaning the graph is going to hit it and then turn back around. So if I have this graph, x is equal to -3, so this is an x-intercept, so I know it crosses the x-axis at this point. It's a positive, so it means it's going to go up. So my parabola will look like this. Notice that here, that is our repeat at 0, or our double root, which again is a repeat at 0. When we have this repeat at 0, it means that the graph hits that x-intercept and then goes back the opposite direction. So it doesn't exactly cross it. And so that's what a repeat at 0 is. So make sure that you take note about that, because we will have graphs where we have to look at that. And so we can use all this knowledge to help us sketch this graph. So here I have a cubic, x to the third minus x squared minus 2x. I want to graph this function. Now before, you probably had stuff like this, where we had x and y, and you think of some x's, and you graph it, you find y's, and you connect the dots. For us, we want to look at three things. We want to find the x-intercepts, we want to find the y-intercepts, and we want to look at that end behavior, that table that we had previously looked at. So let's first find the x-intercepts. So the x-intercepts, we make y 0, okay? Now this looks difficult because it's a cubic, and so we can't factor it. Well, factor it into two binomials. However, if you realize that there's a greatest common factor of x, each term has an x value, I can factor that out, so I get x squared minus x minus 2. And now I have a quadratic that I can factor into two binomials. So when I factor that quadratic, I get x minus 2 and x plus 1. Now this is key. I have three factors here. So I set all three factors equal to 0. X equals 0, x minus 2 is equal to 0, and x plus 1 is equal to 0. So that gives me that x is equal to 0, x is equal to 2, and x is equal to -1. The x-intercepts would be 0, 0, 2, 0, and -1, 0. So if I plot these points, they're all going to be relatively close to each other. Now let's find the y-intercept. Well, if the x-intercept is where y is 0, the y-intercept is where x is 0. So I'm just going to make x 0. Now when I do that, I get y 0. So the point is going to be 0, 0. And we don't actually need to show this if we realize that when we found the x-intercept, we actually already found the y-intercept to be 0, 0. Because we can't cross that y-axis more than once. And then finally, the end behavior. Well, for our end behavior, we have to look at the degree, and we have to look at the leading coefficient. Well, the degree is odd, and the leading coefficient is positive. Right? This is a positive x to the third. So if I look back at my notes and my table, the degree is odd and the leading coefficient is positive. So as x goes to infinity, y is going to go to infinity. As x goes to negative infinity, y is going to go to negative infinity. It's going to look like this. They're going to go in opposite directions. So after my x-intercept to the right, I know I'm going to go up, and it's going to keep going up. After my x-intercept to the left, it's going to go down and keep going down. Now, it must turn around here. So it's going to go up and down. And then somewhere down in here, it's going to turn around. So it's going to go up and down. Now, this is not a perfect graph. It's not great. And you could have this turning point here, or maybe it goes really large like that, or maybe just a little jump like that. For this class, you don't have to be too specific. These are the three things we want to find: end behavior, x-intercept, y-intercept. Everything in between, you just fill in the gap. And you can check on a graphing calculator or software to help you out. All right, so we want to sketch a graph of these polynomial functions. So just like we did before, we want to find the x-intercepts, the y-intercepts, and the end behavior. So I'm going to factor this to find the x-intercepts. So 0, x squared, plus 3x minus 4. And I can see that I'm going to have, sorry, that's y. I did not factor out a 0, factor out an x. That's what I'm confused about. There we go. Okay, so we're going to have 0 is equal to x times x plus 4 times x minus 1. So that gives us x-intercepts of 0, 0, negative 4, 1, 2, 3, 4, and positive 1. If I find the y-intercept, I make x 0. Again, we can see that it crosses the origin, so that's the y-intercept. The degree is odd, which means that the end behavior is going to go in different directions, and the leading coefficient is positive. So that means positive to positive, negative to negative. We're going to have these turning points, and that's my graph. Over here for the second problem, notice we have this negative. When I factor out to find the x-intercepts, what I'm going to do is I'm going to factor out a negative x, and it's a squared. So that's the greatest common factor. I'm going to factor out that negative x squared. So now I'm left with, 2. I'm left with 2x squared plus x minus 3. And so now I have to factor this. So I get 0 is equal to negative x squared. That looks like a negative negative. Let me rewrite that. I'm going to have these two factors. 2 and 3 are both prime numbers, so that's very helpful. So I'm going to have 2x and x. And where's that 3 going to go? I believe it's going to go here. So I'm going to have a positive 3x minus a 2x to give me that positive x. Now, if I set these equal to 0, I'm going to get x is equal to 0, x is equal to positive 1, and x is equal to negative 3/2, which is negative 1/2. The degree is even, and the leading coefficient is positive. So that means that we're going to go down in both directions. Now, this is the important part. Notice this right here. This gives me negative x squared is equal to 0. So x is equal to 0 and x is equal to 0. I get that double root. So that double root means that at this point, it's going to hit the x-axis and bounce back up. So I'm going to have this sort of M-shaped graph. Be very, very careful about this double root, because if you didn't catch that, you just draw this right through, and then you'd have to draw it back up again. What would happen? So don't be confused with that. Just understand that a double root means you're going to hit this x-axis and go right back and change directions. All right, and that's going to be it for graphing polynomial functions. So again, the key is find your x-intercepts, find your y-intercepts, and know the end behavior.